I will put this talk into the context of the problem of taking the continuum limit or of defining the continuum limit. So that's why it's from discretum to continuum. And as was mentioned, that is one of the key problems in a number of approaches in quantum gravity. Let me also say that so this result is together with Valentin Bonsomme, which resides in Paris, and there's some follow-up paper to appear. Just to mention the overview, so that I will basically tell you that the boundary functional, that is a partition function with boundary, is very important and could be actually seen as fundamentally defining the theory. I will then review the continuum results, to, which basically define dualities for 3D gravity, then a short review on Ricci calculus, and then we go to the main subject of the talk. Okay, so to give you this context of the problem to define the continuum theory, there's this question of how to formulate a theory of quantum gravity. Now I present you a setup which is extremely convenient and practical in order to discuss the continuum limit and such theories as loop quantum gravity and spin foams or Ricci calculus and other non-perturbative approaches. So in my understanding, you have a theory of quantum gravity if you have a prescription for basically giving me the partition function, which, however, has to act on boundary data. So it's a partition function with boundary. And it comes with many names. So it's a partition function with boundary, or transition amplitudes, or vacuum wave function, and so on. So this is really that you only refer to the boundary, and you want to define the partition function as a function of this boundary. And of course, you want to regain the semi-classical limit. So you should get in this limit basically back the Einstein-Hilbert action. So this should encode the full dynamics, and it only refers to the boundary. So at some naive level, there's some holographic case to it. And we will get more detailed what we mean with that later on. And as I will explain you on the next slide, it's also a practical definition which you can use for setting up a truncation scheme, because it's easier to get basically this partition function for certain types of data, and these certain types of data describe your homogeneous geometries. So that is basically infrared modes, and then you can basically work towards a truncation scheme where you take more and more inhomogeneous data or UV modes into account. So you do already take them into account in the dynamics in the bulk, but this is really about getting this functional on the boundary in a consistent way. And so that's basically to say the boundary is important. And let me basically give you a taste of how you can formulate the continuum limit in terms which look discrete. And that now is a standard technique, and especially in loop quantum gravity, that you have Hilbert spaces which are based on discrete structures. Now we can always understand these Hilbert spaces as part of a continuum Hilbert space in a construction that is known as inductive limit. And that works by basically specifying certain so-called embedding maps, which allow you to embed these Hilbert spaces which can support less complicated wave functions into a Hilbert space which supports more complicated wave functions. And this embedding map is really important, because actually it does specify your notion of vacuum, which you have to add to the additional degrees of freedom in these more complicated wave functions to define this embedding. So you basically have these embeddings which have to satisfy very strong conditions. And the continuum limit is defined by allowing arbitrary fine refinements. So this alone would be just a kinematical setup. But what you actually now want to have is basically really the amplitudes, that is a partition function, as a functional of data you can put on these discrete structures, or equivalently as a functional on this Hilbert space, so as a linear functional on these wave functions. And you can define these functional on each Hilbert space separately, but they do have, again, to satisfy a very strong condition, which is known as cylindrical consistency. Namely, if you, for instance, consider here this functional on a very complicated, basically in this large Hilbert space, and you evaluate this functional on a wave function, which comes from this lower complexity Hilbert space, so it comes from embedding this thing, then you have to regain basically the same value for this functional evaluated on the same wave function. So technically it's a pullback condition which you have here, and you want that this condition holds for all these amplitudes. That defines the amplitude really as an object of the continuum theory. At the same time, you can show that this complete family of consistent amplitudes, if you can define that for arbitrary complicated refinements, and it is cylindrically consistent, this is equivalent to having a complete renormalization trajectory of your system. So you do get basically the dynamics, which is already integrated out because we are not referring to the bulk here, for all from UV to infrared, where UV and infrared, the notion of scale is defined by the complexity of these wave functions. Okay, so this is to motivate that refining the boundary is important, and this hasn't been taken into consideration too much, because usually if one speaks about the continuum limit, that's quite often just referring to the bulk. Let me just tell you how this is different from maybe an older and more naive viewpoint, which is to say, oh, I define the amplitude just on some kind of fundamental building block, which most often is a simplex, and sometimes referred to as space-time atom. And so you define basically this so-called fundamental amplitude, which is nothing else than also the partition function with the boundary for this very kind of low complexity kind of boundary data. And then the description is you get to more complicated setup by gluing more fundamental building blocks, for instance, for a geometry which looks like this guy. However, that's a very incomplete description. So basically, here you have to choose, via gluing, you choose to glue somehow all these fundamental building blocks to a triangulation, and the question is, what is the meaning of this triangulation if you are not triangulation invariant? And there's one popular suggestion to sum over triangulations, which a priori is also completely undefined, and you have to specify how. And Daniela was discussing yesterday the group field theory approach, and there's a question whether this can be also specified, the dynamics of it, by this partition function as function of the boundary data. So I do think it also fits in this description. So if you do not sum, but say, okay, I refine because I assume that my results will converge, this model actually implies a strong form of locality, which in 4D always breaks the diffeomorphism invariance. And so the only one way out is to go to non-local models. But if you have non-local actions, then actually the question is, what is the meaning of a fundamental building block? Actually, it loses sense, actually. However, if you use these boundary functionals, that's a convenient way to deal actually with non-local models, also in renormalization. So there's the slogans, which are a bit more slogan-like and you can't read, which is to forget space-time atoms, at least the naive form of it, because it's really that the entire dynamics is encoded in this boundary functionals. Okay, so here as a side remark, you can ask what should this boundary functional satisfy? There's one property, the gluing property, from which you can derive all kinds of nice properties which you want to have, among them Hamiltonian constraint and consistent algebra of these Hamiltonian constraints. And I won't have time to explain you that, but you can always ask me, of course. And that finishes the motivation for you to be interested in boundary functionals. And now we are coming to the subject of holography. So we only now refer to the boundary in defining our theory and trying to define our theory. So what does it have to do with holography? Actually, so that would be just kind of to naively say that you have something holographic. There's a non-trivial condition, which is, can this quantum gravity dynamics, which is encoded in this boundary functional, be encoded as a field theory, which is coupled to the boundary metric defined on the boundary? And the very non-trivial question is if this field theory is actually local, because you can always reach some kind of non-local dual field theory, which we might discuss at the end how you do that, but you might get an idea of about that. And so the definition of the dual field theory is that basically integrating out this dual field, which is coupled to the boundary metric, that gives you a functional of the boundary metric, and that should give you back the partition function of your boundary metric coming from quantum gravity. Okay, so having these things, there's a question of what is the relation to all these more known frameworks of ADS, CFT, dualities, and so on, where, of course, the main issue is that these are all defined so far for asymptotic boundaries, whereas here we deal with finite boundaries. So that's one of the main new aspect, which I have to say we can treat here because we do topological theory in 3D, but it's interesting to see that actually these things work out. So the general question is actually what can we say about the finite boundary functional? So it's really trying to compute this finite boundary functional, and that's actually the reason why we first looked at it in 3D, because it's to compute something. And 4D, some aspects are in progress. Okay, I'm still in motivation report. So, so here it's, it's really to, my aim here is really to provide a concrete model for holography starting with quantum gravity model. So usually it starts the other way around with a conjecture, but here it's really starting with a quantum gravity model, derive your dual field theory. And that's also in this context of discrete approaches. So we really work with an explicit realization of 3D quantum gravity. There's this puzzle which Steve worked a lot on, which is 3D gravity is topological. So you could wonder, and I did a long time ago, how do you get to a field theory on this dual field theory? There's a further motivation, which was an invitation to the community, which is if you can use dualities, that's a very strong tool, it seems. So it really would be really helpful if you can see whether we can use it in a non-perturbative setup or whether they are not so useful. Okay. So now let me basically give you the context of this concrete model. And that what started with a paper which appeared 2015 on the one loop partition function of 3D quantum gravity, which has been computed. And here's just a short historic, completely incomplete overview. So, so 3D gravity CFT correspondence. There's one initial point, which is this Brown-Henault paper on showing that you get a central extension, and so Virasoro algebra related to CFT from asymptotic conditions in ADS spacetime, and that has been 3D. Gerard came up with a holographic principle. Then, of course, there was ADS CFT, which sparked a lot of activities. And there's one paper where Giombi, Maloney, and Yin computed the one loop partition function for EDS gravity in a specific setup and showed that this reproduces the character of the Virasoro algebra. And because it exactly reproduces the character of the Virasoro algebra, the argument is that also this one loop partition function is actually exact, so you don't get any higher order corrections. Then, in particular, Barnish and his group worked a lot on extending these kind of results and asymptotic discussions to flat space, and it's lots of papers. It went on for a long time. And so recently, this computation has been done in a flat context where from a technical level is actually much simpler. And one could show that it reproduces the character of the BMS group, but just that these BMS group representations have been only very recently defined by a apparently very able student, Oblak, of Barnich. Okay. So this one-loop computation has been done for a certain topology, which is describing a background matrix known as thermal spinning flat space. So this is a piece of flat space. You write it in cylindrical symmetric coordinates. So here you have a cylinder, and there's two non-trivial parameters. One will be the length of the cylinder, which will define you the temperature or the inverse temperature beta. And the other is that to have a spinning in this here, that you do identify this cylinder to a torus, but you do it with a certain twist. And this twist angle I will call alpha. And you want to study the partition function as a function of just these two parameters and the flat boundary metric usually here just of the integral over this path integral over matrix satisfying these boundary condition, which is this flat metric here on the boundary. So the classical limit is just given by evaluating the action, which with a standard boundary term, which I've chosen here. And the computation is straightforward to do. So if you have a homogeneous geometry here, it's actually flat geometry, and the extrinsic curvature is homogeneous. You just get this result that you get minus beta divided by 4g, and no alpha dependence. And we will work with this boundary term. However, the thermodynamic interpretation and this matching the Virasoro character works actually with a slightly different boundary term, which is, however, only well defined if you do this asymptotic, if you consider an asymptotic limit. For that reason, we will actually work with this other boundary term, which is defined for finite boundary. Okay, and I can comment more on this other boundary term, which actually comes from Chern-Simons theory in the end, or if you ask me. Okay, so for one loop, you need the background action. We have discussed that, and that the correction is a one-loop correction, which is basically the action as a determinant of the Hessian. And basically here I give you a 5 seconds overview of how this has been computed. So here you don't really specify any boundary data. You really go on and do perturbative quantum gravity in writing basically your measure term and after gauge fixing. So you get a bunch of Laplacians, and you try to evaluate the determinant of this action by using heat kernel methods. And to implement this particular periodic identification, one uses a method of images. And that gives you a certain summation over images of the action of the group. That leads to the sum over this k value below. So after you've done that, you get this one loop correction, which mostly is infinity. So they do regularize it by saying, okay, we add a small imaginary epsilon here, and I spoke to Oblak, and he actually was asking me how we regularize it, or do we have a reason to regularize it. They don't actually know, but this is always infinite. I mean, you can see that for any rational number you get 1 over 0, and we will also see that in the discrete approach, but not for all discretizations. Okay. So this calculation is really using standard field theory. In some sense, it doesn't use the topological nature of the theory. So can we change that? Can we really understand better the contributing degrees of freedom and the structure of the result? Why do we get the summation starting with k equal to 2? Can we do that for finite boundaries and actually include boundary fluctuations? Okay. So we will address basically a similar calculation which goes farther, because we will do that for finite boundaries and for boundary fluctuations of the metric in terms using discrete methods. And actually it's much more straightforward and maybe nicer. And we will use Ricci calculus, which in this context is the semi-classical limit of spin forms. There has been a pioneering paper on linearized Ricci calculus, which is important here in this context of one-loop corrections by Rocek and Williams back in '81. And indeed, that introduced lots of techniques. It wasn't discussing boundaries. At some point, I was involved in a paper which indeed was also involving boundaries. But we will see that Ricci calculus is ideally suited in calculating partition functions with boundaries, which even in 3D is a surprisingly hard problem, actually. Okay, Ricci calculus is basically a discretization of general relativity. You choose a triangulation, you attach variables to the triangulation, lengths of the edges, and this triangulation is piecewise linear. So the length of the edges in this context will uniquely define you the geometry, where these deficit angles give you basically the curvature in these triangulations. You can already, here you have the Ricci action, and you can already see that the boundary term here looks very similar to the bulk term. And indeed, it turns out that Ricci calculus in 3D is already allowing you to compute actually the continuum Hamilton-Jacobi functional. So the continuum action evaluated on a solution for piecewise linear boundary data. So basically you can take the Ricci action and consider the equation of motion. And you do find the same equation of motion as in the continuum. There's also a similar trick happening in the continuum, that it turns out that the variation of the curvature term drops out, so you just have that you are left with the deficit angle, which gives you curvature, is vanishing. So that means that you do just have the boundary term if you evaluate the action on a solution. And this term is independent of your choice of bulk triangulation. As long as it's flat, you do get the same kind of dihedral angles here. So this Hamilton-Jacobi function turns out to be really the function of continuum general relativity for piecewise flat boundary data. And actually, together with the local form of the action, it shows you the topological nature of the theory. So here, Ricci calculus, I mean, that's the message you should take from that is that we can easily deal with boundaries in Ricci calculus. And that was classical theory. We come now to the quantum setup, where there has been a long discussion on the measure in Ricci calculus, which I don't want to get into it. The point is that in 3D, there is a preferred measure, which is that you want this measure to reproduce the symmetries of the classical action. And this symmetry includes triangulation invariance. So you want this measure to be triangulation invariant. And Sebastian managed to figure that out here in the audience. And this is the measure you get if you require triangulation invariance for the linearized Ricci action. And nicely, it actually reproduces the measure you actually do get in spin forms. So that means that you can actually compute in Ricci calculus the one-loop partition function using discrete methods, and you are sure that you reproduce the continuum result. It actually means that you can even use a very coarse triangulation, as long as this coarse triangulation is just a coarse boundary bulk triangulation. Okay? One important remark is that Ricci calculus has a notion of diffeomorphism symmetry in flat space, if you consider flat space solution. And that is, if you imagine you triangulate flat space, you can take any vertex of this triangulation and move it around in this embedding flat space. And this has been discussed already in this pioneering paper by Rocek and Williams. And this is basically a discrete remnant of the continuum diffeomorphism symmetry, and we will have to gauge fix this later on. So unfortunately, that is actually turns out to be broken in 4D if you go to solution with curvatures. And a reason why 4D is much more complicated. So let's go on and try to really just compute this one loop partition function with finite boundary and later on with boundary fluctuations. So as I mentioned, we can choose a triangulation which is the coarsest one we can imagine, but we still want to allow for a continuum limit on the boundary. And here's a triangulation. You have basically a huge cake. You can slice this cake into pieces. So you get prism. Each prism you can subdivide into 3 tetrahedra. So we will get only one time axis, which is this kind of triangulated 1D line. And then we have these prisms. And this is kind of background triangulation. For flat space, there's one condition to get flat space, which is that the deficit angle at this axis should vanish. That gives you one condition between this length of one in the angular direction of one prism here and the radius of your cylinder. Okay, which is this one, and this will define a parameter which has to go to 0 in the continuum limit on the boundary. So the classical radiation can be evaluated, and you can do that on any kind of coarse boundary triangulation even, and it reproduces a continuum result. So that's kind of just some topological nature which you see here. So that is done. We just need to think about the one loop partition function for the finite boundary now, which comes from the determinant of the Hessian. So we need the Hessian of the radiation. We expect that it codes a second order difference operator, which we basically know from doing previous stuff. And to basically make it, to be able to deal with that, we have to apply Fourier transform to decouple these modes. Okay, and there's only one non-trivial point about the Fourier transform. So we do that as follows. We have variables which are basically fluctuation variables. So we need to also expand the radiation first in fluctuations for these fluctuation variables for the length of these edges. We then resort these variables so that each vertex comes with a number of length variables attached to it. So basically, for this vertex, we have this diagonal, we have the radius here. These are the two bulk edges. And then we have also the time axis, which doesn't come with an angular dependence. So we just have one of these time edges for every time step, of course. And then in addition, we have these boundary variables, which will come later. And there's also 3 boundary variables per vertex. So having reordered our boundary fluctuations in this way, we just define the standard discrete Fourier transform with one little thing, with one little twist, which is we do a twist in the periodic identification of our cylinder. So to accommodate that, we have a little twisting parameter here. And if you do that in this way, it defines your shifted time frequency, which will always turn up. But you need to do that to really get the Fourier transform decoupling all of your modes. So otherwise, you wouldn't really have decoupling modes. And then all the dynamics or the second order action is encoded in this matrix M. And we basically have to take this determinant of this matrix M. And now it's just depending on the number of variables per vertex. So here is just a little piece of this already written in a very convenient form after somebody has sat down and computed that for 3 weeks. And then found out that you can compute it in 2 hours. But so this is only the part for the bulk variables. So t is not so much important, and will basically, because there's only one t, it comes with this Kronecker delta and for k equal to 0. That will actually drop out. So the entire determinant will come from this 2 by 2 matrix, actually. You see the lattice Laplacian with a little index k. This is the Laplacian in angular direction. We are a bit puzzled because there's only delta k. There's a very weak coupling in time direction, which is only sitting here, which is omega nu, which are these time frequencies. So these do a coupling in one step between two time slices, between two neighboring time slices, but it's multiplied with a. So you could be a bit worried because you only get something non-trivial in this twisting angle if you have a coupling in time. And indeed, if you put a equal to 0, do a continuum limit, you would get a completely wrong result. But in fact, one could already see here, if one integrates out one of these variables, the stuff in green defines your matrix which has 0 determinant. Okay, so there's much more terms here which are basically about the boundary fluctuations. Let me discuss the null vectors because that will explain the structure of the results. So I said for every bulk vertex you have basically this the symmetry related to moving this bulk vertex around. So you can move this vertex in time direction. That defines you a k equal to 0 mode. So k equal to 0 modes are involved in this diffeomorphin symmetry and will be actually completely killed by this diffeomorphin symmetry. And you can move around this vertex in one hypersurface here, and that only involves the k equal to -1 and the k equal to +1 modes. So there's only these 3 modes affected by gauge symmetry. They don't affect the d variables for k bigger, larger than 0. So we can integrate out the d modes, and look what happens. If we do that, we just are left with one by one matrix. And then we end up with basically Laplacian in time direction. So it's a Laplacian in time direction with a little twist to it. And then there's some subleading term, which will not be important. So it's straightforward to compute the determinant here of this Laplacian. It's a diagonal matrix for all these modes. If you take the product of these things, you do get now something which depends on this twisting angle alpha. Okay, and the higher order and A terms are higher order, and you can deal with it. So finally, you can put all these results, which are non-trivial, with a non-trivial dependence in alpha together, and you do find basically this result, which if you put q equal to exponential of I alpha, reproduces actually the continuum result up to, of course, a certain UV cutoff here. So you can do this calculation at finite boundary. You reproduce this result. It explains you why this starts at k equal to 2. That comes from the diffeomorphin symmetry of the bulk vertices. There's a point of it, to represent a certain angle alpha, which is, say, rational by p over q times 2 pi, you need at least q discretization steps. And if you leave it there, you do get a finite result. If you increase, if you do two q steps, you will also get an infinite result, because you also you find a 0 here, a 1 over 0. And it seems that indeed the contributing degrees of freedom are the radial edges attached to the boundary, and we will confirm that with calculating, actually finding the dual field theory. We need to take the continuum limit in angular direction, at least to some extent, as we have seen. Here we don't need to take any continuum limit in time direction, actually. Okay. So in the time that is not too much and left, let me discuss boundary fluctuations. So now let's try to compute this partition function for a slightly more complicated boundary geometry. So you allow the boundary metric to fluctuate. So it doesn't need to be flat anymore. So basically, there's basically the geometry of the boundary is defined just by the conformal mode. So you can basically, in an embedding picture, imagine that these are little bumps here, and this is basically the conformal mode for this 2D boundary metric. And you just get this boundary term. That seems to be easy to get, but it's actually harder than you expect to evaluate in terms of the boundary metric only, because you do get a nonlinear, non-local functional. Now there are lots of discussion in the context of ADS-CFT, also for the 3D setup. In particular, Steve argued for, in this case, that degrees of freedom should come from breaking 3D diffeomorphism symmetry by this boundary. And we will confirm this picture. Here the arguments, we are really using ADS and the asymptotic expansion based on this Pfefferman-Graham results. So these discussions suggest that our radial variable is related to indeed a dual field theory, maybe of Liouville type. So it's actually now, since you have the Hessian, that was a complicated work, it's straightforward to find the effective action as a functional of the boundary metric. Here it is. It doesn't tell you much, but the only thing you should see is what I've done here. I've taken the continuum limit. So k squared and v squared are actually really the wave vectors. And you should see that you have 1 over v squared. So what you get is really a nonlinear functional of the boundary metric, which appears quite often. And then I have also written here these parts. I have separated them because there's a radial displacement mode, so it's vertex going in outward or inward. That's one piece. But the other piece are actually coming from displacing the vertex on the boundary tangential to the boundary. So it's actually boundary diffeomorphisms. So we were actually quite puzzled for some time, but it turns out to have a consistent reason. The reason is that you do get boundary diffeomorphism contributing because you have a non-vanishing first order part for the boundary action. It's this one. And to make that the boundary diffeomorphism invariant, if you would sum up the entire perturbation series, you do get these boundary diffeomorphism things contributing to second order. On the other hand, we can reproduce them by requiring boundary diffeomorphism symmetry from the first order term. So basically, physically, we can actually kind of gauge fix or set these boundary diffeomorphism modes to 0. Okay, having the discrete result, now we say, can we compute it in the continuum, at least perturbatively? And after lots of expansions of all these actions, yes, you can. And luckily, it completely matches the discrete result. And here you see it a bit more nicely if you express it really in terms of the metric. This is now the 3D metric, which is a solution. So you can be expressed to linear order as a diffeomorphism here. And you have diffeomorphism in 3 directions now, in radial direction. And in the boundary diffeomorphisms, here you just get the Laplacian in time direction. Okay? And you can rewrite that into boundary metric modes, and then it becomes actually non-local. So let me maybe get to the main point, which is, okay, now we want to basically reproduce this result we got. So this would give you basically the one-loop partition function with boundary data by a dual field theory on the boundary. So we guessed some field theory. It's just here is a kinetic term, so free field. It's not actually it's not a free field because it's actually coupled to the curvature, so the 2D curvature of the boundary. So we expanded that to second order, we discretized it. You get a lot of exercise in doing this. And after integrating out this phi field, you do get this following effective action, which is again a function of the boundary metric. That's the action. Now compare that with basically the one non-trivial mode, which was the radial mode. And if you look closely, which you might not be able to because it's too small, you can match these two terms completely, even on the discrete level, by fixing this coupling here, and by only having the time Laplacian and time direction in this kinetic term. So we did identify this dual field theory, and it's local. And it's a bit puzzling that it is only the time direction which shows up here, but it seems to match a flat limit result which comes from ADS by Barnish et al., which wrote like two versions of, I think, of conformally invariant results you can have, and one version is exactly this one with just the Laplacian time direction. So now here's a simple explanation of what is happening. There's even more you can say, because in this setup, before integrating out the phi field, the matrix you get completely matches basically the part responsible for the radial mode, which you got from the gravity case. And in this case, you only had the radial variables. So actually the phi mode, the phi field, you can indeed identify with the radial edges. So this is basically that you indeed can identify geometry from the boundary field theory, which basically is the main open problem in holographic approaches in higher dimensions, and it completely confirms Steve's viewpoint on which he had in 2005. So here you can actually extremely nicely show that, and it's a bit harder to do it in the continuum because it's kind of the geodesic distance from the boundary to some center, which is a bit harder to express in the continuum theory. But in Recce, in this setup, it's basically for free. And a heuristic argument based on Recce calculus suggests that actually that happens in all kinds of setups. There's an easy argument: as long as you have some kind of spherical topology, you should get a completely local boundary field action, where this field, the dual field theory, you can always identify with the edges going to some center of your bike. And we want to confirm that, which is kind of a paper to be finished. Okay, I'm second to last slide. So that basically is kind of the main point if it comes to dualities. So we basically did show here, starting from a kind of discrete calculation, that we can regain this dual field theory. You can generalize this entire calculation to a DS or the ADS background by using a modified version of Recce calculus where you use homogeneously curved tetrahedra. There's a very interesting question, which is, can you reproduce it in a full non-perturbative setup in spin forms? It leads to an interesting problem, which is spin network evaluation of boundary spin networks. Mathematically, even is discussed by mathematicians in the asymptotic limit, so it is certainly non-trivial. But we have the hope that this could be attacked by using integrability methods. So that is an interesting, very interesting stuff to look at. And doing that would allow us to use that as a toy model, tackling important questions for the continuum limit, because here you have discrete spectra, but you want to take the continuum limit on the boundary, so you can study what happens in this case. It's basically that you have a boundary theory with propagating modes, so it's a simple version of the full 4D setup you want to tackle. Okay. So basically, I hope I have convinced you that in 3D, discrete models provide an elegant method to evaluate partition functions. So it gave us much more insight than the continuum calculation. it gives you an explicit model for holography. All these things did work to a certain extent because we had a topological field theory. We are now trying to use it also to study how much can we do in 4D in Ricci calculus with boundary. And it provides this toy model to understand the continuum limit in a background-independent context. And we have this nice interpretation that, in fact, the radial edges can be identified with Liouville-type fields. I do have... so there are many further directions to explore, which I leave here. I say that it's non-trivial to show it's local because you could basically always say that you identify the boundary field theory with some kind of bulk variables and integrate out the rest, and then you in general get some non-local mass. So that seems to be, kind of an almost trivial tautological statement that you can express it as some kind of completely non-local field theory. So here indeed the non-trivial part was to say at least there exists a local form of this boundary field theory.
More comments or questions? Okay. If not, let's close this session now and go for coffee. And please be back in half an hour.
Thank you. Please let me know if my voice begins to fade, and I'll try to talk louder. I'm just getting over a case of bronchitis. I almost canceled my trip here, but so far I'm very glad that I didn't. I thank the organizers for inviting me to what seems to be a very nice conference. The basic question that I want to address today is one that sounds as if it should be simple. How many dimensions is our space-time? What I hope to convince you at a minimum is that it's a much harder question than it sounds, not only as a question to answer, but even as a question to pose in a way that makes sense physically. So we certainly don't know the answer to this, but there are some pretty strong indications that whatever the answer is, it is scale dependent. And there are some interesting hints that, in particular, near the Planck scale, the dimension of space-time effectively becomes 2. And at the end of the talk, I will do some wild hand-waving to try to give you some ideas of why that might be true. But of course, we don't know, and perhaps someone here will come up with less hand-wavy ideas. So in classical general relativity, this is a question that is simple to answer, because we start by modeling space-time as a smooth manifold. That manifold has some topological dimension. That's the answer. The idea that this might change with scale is also an old one, going back to Kaluza and Klein, and actually I just learned before either of them, Nordstrom, that perhaps at small enough scales, the dimension of space-time might be larger. And of course, by now, this is standard in string theory and brain cosmology. But again, there's no great mystery involved. The space-time is still modeled as a smooth manifold with some dimension, say 4 plus d. If you're looking at scales smaller than the scales of the extra dimension, you see the full 4 plus d. If you're looking at larger scales, you don't see the smaller dimensions. What is interesting to me, what got me interested in this, is the hints from a number of different approaches to quantum gravity that near the Planck scale there's actually a reduction in dimension, typically to d equals 2. We don't know how to quantize gravity. And one of the best ways, in my opinion, to get hints of what's going on is to look at the circumstances in which different quantization programs lead to the same outcome, because then that might reflect something that is really a property of the ultimate theory, which we don't know. And so this is one of those areas that seems at least worth exploring. Yeah.
Between colors of time, wherein the dimensions actually increase, like
Yeah.
26 and so on. And the third bullet,
Right.
the difference is quantum.
Probably. Yeah, the difference is probably quantum, although you can certainly construct classical models of this sort. For example, if you just take a space-time in which you have some lower dimensional submanifold, in which you're restricted to some lower dimensional submanifold, but that has wormholes coming off it attached to higher dimensional space-times than when you get to small scale. But
what I meant to ask is that if you ask the string theorists, they say the 2D is a different thing from the space-time
no,
dimension.
well, yes, it's true that the world sheet dimension is, that's a completely separate issue. Although, if you ask a string theorist, they will also tell you that if you have a gas of strings at a high enough temperature, the number of degrees of freedom drops to that of a two-dimensional field theory. I'll come back to that later.
So do you need high temperature and quantum? Okay, we're here.
Okay. So, in order to answer any of these questions, you first have to decide what you mean by dimension. And this is not at all an easy question. Even at the level of ordinary quantum mechanics of a single particle, if you look at the path integral, you find that the path integral is dominated by paths that are nowhere continuous and that have fractal dimension. It's only in the semi-classical limit, only when you take a sum over paths, that you find an approximately smooth path that really looks one-dimensional. In quantum field theory, in some sense, things are even worse. The path integrals are typically dominated by configurations that are not only nowhere smooth, but nowhere continuous. And if quantum gravity is quantum at some deep level, and our observed smooth space-time emerges from some different quantum structure, then we should expect the same there, that if space-time is not the fundamental ingredient, then its dimension isn't either. So this means that we need a dimension operator, and it's not so clear what that means. In general, what people do is to use what are sometimes called dimensional estimators. That is, quantities that first of all can be defined in a quantum theory, that can be made into quantum operators, quantities whose spectrum or expectation value has a simple and well understood dependence on dimension in the cases that we know what dimension means, and that can be plausibly generalized to broader situations in which it's less clear what we mean by dimension. Now, there is more than one such choice, and in the next couple of slides I'll go through some of the dimensional estimators that people have used. It is not obvious that these all will agree with each other in a given quantum theory. They agree classically by construction because they're supposed to give the ordinary dimension. But in a quantum theory, it may be that the answer to what is the dimension of space-time is that it depends on exactly what you mean by dimension. It depends on exactly what question about space-time you're asking. So let me go through some examples of standard dimensional estimators. And I've included all of the ones that I could think of that have been used in this context. But if people know of others, let me know, because eventually I'll have to write this up, and I'd like to get as good a list as I can. So the most straightforward dimensional estimators are more or less directly geometrical. For example, if you look at a geodesic sphere of radius r and compute its volume, if at some scale, at some range of r, the volume goes up as r to some d power, then d is a measure of dimension. Now, what that means in quantum mechanics, it could mean several things. It could mean that the spectrum of the volume, it could mean that this is true as an operator statement. It could mean that it's true as a statement about the spectra of the operators. It could mean that the expectation value of V is either the expectation value of R to the D power or the expectation value of the operator R to the D. All of those are perhaps subtly different. Probably in most cases they'll give you the same dimension, but you have to be a little bit careful. Now, notice that this, like a number of the other dimensional estimators that I'll be talking about, requires that R and V be well defined as quantum operators. So you need a notion of lengths and volumes as observables. And notice also, of course, there are generalizations. For example, if you have a volume operator and an area operator, you can look at volume as a function of area and get the same kind of information. And notice also that this can vary with scale. Again, the simplest example is the Kaluza-Klein theory, where if R is smaller than the typical size of a compact dimension, you'll see all of the dimensions. If R is larger, then as you increase the size of your geodesic balls, you'll only be expanding in the large dimensions. So this will give you a lower value of D. A related, somewhat more general and somewhat more mathematically sophisticated dimensional estimator is the Hausdorff dimension, which is a similar construction, but which asks how many geodesic balls of radius r it takes to cover a given region. And again, that will grow as some power that depends on the dimension. Spectral dimension, for now I'm going to treat this as a geometric dimension, although I'll come back to that later. Spectral dimension is one of the ones that you've heard about before in this conference. The idea is that if you can define a random walk or a diffusion process on a classical manifold, the probability for diffusion from, say, x to x prime in a time s has a standard form that's true regardless of the geometry of the manifold. It depends on a coefficient with a power. It depends on the square geodesic distance, sigma, between x and x prime. And it has corrections that depend on curvature, but that are also known. So given that that holds for a smooth manifold, we can define dimensions by just saying, look at this same expression for whatever space-time we're looking at. And in particular, if we look at the return probability, the geodesic distance drops out. And so that allows you to define a dimension without requiring a notion of geodesics or distance. There is another dimensional estimator that you can also get from the random walk or the heat kernel. This is called the walk dimension, and that's simply a measure of, in a time s, how far on the average does an object diffuse out from its original location. So the basic idea is that the higher the number of dimensions, the slower the object will move out from its original location, but also the longer it will take to get back to its original location because it has more dimensions to move. Now, those dimensional estimators are implicitly or explicitly require metric with Riemannian signature, positive definite metric. And you might worry, as some people have, that maybe analytically continuing to Riemannian metric might distort some of the physics. So it would be good to also have some explicitly Lorentzian dimensional estimators. And there are a few candidates. One of them is what's called the causal spectral dimension. The idea here is that you start with two random walkers, and you measure the amount of time for them to meet. Each of them can be moving causally, and you don't need to continue to Riemannian signature for this to make sense. The Myrheim-Meyer dimension, as far as I know, has only been used in causal set theory, but people ought to look at using this in other circumstances. The Myrheim-Meyer dimension is based on sizes of Alexandrov neighborhoods, or causal diamonds. A causal diamond is just the intersection of the future of one point with the past of another. And the Myrheim-Meyer dimension basically compares the number of points in a causal diamond with the number of pairs of causally connected points. So for example, in this causal diamond, here's one point. Everything in its future is causally connected. So the Myrheim-Meyer dimension essentially involves integrating the smaller sub-diamonds over the larger diamond. It's easy to see that roughly the number of causally related points should go as the square of the number of points. And you can work out what this is in Minkowski space. It has a particular dependence on dimension and nothing else. Inverting this defines a dimension, Myrheim-Meyer dimension. If you are working in a curved space, the curvature corrections are also known, and there are generalizations of Myrheim-Meyer that include numbers of causal triples and causal quadruples that give corrections that compensate for the curvature corrections here. A third Lorentzian dimensional estimator, and I don't know how to make this quantitative. I wish I did. But you can get information about dimension by simply looking at the behavior of geodesics. There are certain spacetimes, such as regions of Kasner space, and I'll come back to this at the end of the talk, in which, although the spacetime is four-dimensional, if you look at random geodesics starting from some point, they essentially only explore one dimension of the space. So essentially give a two-dimensional spacetime. That is, if you look at the proper distance that a geodesic travels in some given proper time, you find that almost all of the proper distance is in one dimension. Forgot I have this. So those are more or less geometric dimensional estimators. You can also look at dimensional estimators that come more directly from physical processes, which then have less of a direct connection with the geometry, but have the advantage that the physical meaning is much more direct. One standard example along this line is to look at various thermodynamic relations and see how they depend on dimension. For example, in a quantum field theory, the free energy per unit of volume and unit of temperature goes as temperature to the d minus 1, where d is the number of space-time dimensions. And in fact, dimensional reduction in quantum theory was first noticed using this estimator looking at high-temperature string theory. There are similar thermodynamic dimensional estimators that you can construct by using, for example, the equation of state parameter, looking at a photon gas where in 3 dimensions the pressure is 1/3 of the energy density. In 2 dimensions, it's 1/2 of the energy density. So I have 3 spatial dimensions, 2 spatial dimensions. In 1 spatial dimension, the pressure is equal to the energy density. You can look at specific heat. The basic idea is that you have 1/2 kT per degree of freedom, but you have d degrees of freedom if you are in d spatial dimensions. The final dimensional estimator that I know of that has been used is the anomalous dimension in quantum field theory. This is what's relevant in programs like asymptotic safety, which treat quantum gravity as an ordinary quantum field theory. Operators in a quantum field theory have a standard scaling dimension. They're the engineering dimension. I think that's maybe a slightly pejorative term, but that's what quantum field theorists call it. Just a dimension from dimensional analysis. But this gets corrections from quantum corrections. And in particular, the scaling dimensions flow with the renormalization group. So for example, if you look at 2-point functions or Green's functions, a classical Green's function has a standard dependence on dimension. Sigma, again, it's Singh's world function. It's essentially the square of the geodesic distance between x and x prime. And if you know the behavior of Green's function, it's logarithmic in 2 dimensions, you can read off the dimension. This d gets scale-dependent corrections and in a quantum field theory, and that gives you a scale-dependent dimension. Okay, so with these estimators, we can now go back to the original question of what the dimension of space-time is. Now, the idea that this might be scale dependent originally, as far as I know, appeared in a paper by Baylock and Denjo O'Connor in a cosmological setting, but they didn't look at the implications for quantum gravity. They were looking at what they called an effective infrared dimension, large-scale scale dependence. In quantum theory, as far as I know, this was first noticed by Attic and Witten in 1988, who were looking at the behavior of a gas of strings in ordinary bosonic or superstring theory, and discovered that at high temperatures above the Hagedorn phase transition, the number of degrees of freedom, the free energy as a function of temperature drastically changed in a way that amounted to a huge reduction in the number of degrees of freedom. And they even speculated explicitly that that high temperature string theory should look like perhaps a lattice theory, but with a two-dimensional field theory at each site. This was seen, I think, as a peculiar stringy behavior and mostly not noticed by other people doing quantum gravity until a couple of results, one from causal dynamical triangulations, in which it was discovered, I think, much to the surprise of the people who discovered this. Is this fair? Were you expecting? Okay. Well, at least, let's say, much to my surprise, that the spectral dimension in causal dynamical triangulations drops from 4 at large scales to 2 at small scales. At about the same time, people working on asymptotic safety, looking at anomalous dimensions, noticed that if quantum gravity has an ultraviolet fixed point, which is the starting assumption of the asymptotic safety program, that it is necessarily true that the full dimension, the engineering dimension plus the quantum corrections of all operators in the theory are necessarily those of a two-dimensional field theory. So again, as you flow up in energy or down in scale to the UV fixed point, you approach 2 dimensions. After that, that launched a whole range of other explorations that lead to pretty consistent results. If you look at the short distance behavior of the ordinary old-fashioned Wheeler-DeWitt equation and look at the behavior of geodesics, you find this behavior I mentioned before, that even though the space-time is formally 4-dimensional, the wave function is dominated by space-times in which geodesics only explore 2 space-time dimensions. I'm not used to having one of these slide changers. For both loop quantum gravity and spin foams, using geometric and spectral dimensions, there is some evidence that you get reductions to 2 dimensions at short distances, although this is not entirely resolved at this point. In one of the simplest and certainly the earliest non-commutative geometry, Snyder space, if you look at a number of thermodynamic dimensions, you find consistently a reduction to 2 dimensions at high temperatures. In other non-commutative geometries, you can look at spectral dimension. I realized afterwards that this line is not entirely true. The spectral dimension typically changes at small distances. The change, including the direction, whether it decreases or increases, depends on the details of what Laplacian you choose. For models with the generalized uncertainty principle, using polymer quantization, there is a nice result that thermodynamic dimension reduces this time to 2.5 at high temperatures or short distances. For spacetimes with a minimum length, well, there are a number of different ways you can put in a minimum length, but there are particular ways in which the geometric and the spectral dimensions give you a dimensional reduction to 2 at short distances. In causal set theory, which is maybe the simplest framework that you can imagine for quantum gravity, the naive spectral dimension, the spectral dimension from a random walk, actually increases at short distances. But as I said, the spectral dimension depends on the choice of Laplacian, and the Laplacian in the heat kernel that comes from a random walk is not the correct Laplacian in the sense that it doesn't reduce to the ordinary Laplacian in the continuum limit. When you put in the Laplacian that does reduce to, that does have the correct continuum limit, you find that the spectral dimension falls to 2 at short distances. The Myrheim-Meyer dimension for small enough causal sets reduces to approximately to 2 point something. And Green's functions behave logarithmically, again, a sign of two-dimensional behavior at high energies. Finally, if you look at renormalizable modifications of general relativity, which may or may not be unitary, may or may not make physical sense, you find that a modified spectral dimension with a Laplacian appropriate to the particular action, again, reduces to 2 at short distances. Okay, so why? Well, I don't know. It may be that to answer why we need the correct quantum theory of gravity, it may be that these different approaches are giving us different hints at what the right theory is, but that it will take the full theory to really know. But there are a couple of interesting suggestions in the literature, one by me, that might give directions, at least, to try to understand the underlying physics. The first has to do with scale invariance. In asymptotic safety, again, by definition, an ultraviolet fixed point is scale invariant. That's what it means for it to be a fixed point. There is a very general argument that that scale invariance anywhere away from Newton's constant equal to 0 requires that all anomalous dimensions be right to make everything look two-dimensional. The technical details are a little technical, but the underlying reason is actually pretty clear. In a gravitational theory that includes general relativity or reduces to Newtonian gravity, Newton's constant has a dimension and provides a scale. The only way for this to get rid of this scale is either to have Newton's constant go to 0, which gives a Gaussian fixed point, or to have the theory go to 2 dimensions, because uniquely in 2 dimensions, Newton's constant is dimensionless. Now, this isn't in itself a completely satisfying answer, because it doesn't tell you why such a fixed point exists at all. But maybe what you should do is turn the argument backwards to say one of the fundamental symmetries of nature is scale invariance, and this gets broken as you move away from high energies. The second possible physical argument is related to an idea called asymptotic silence. This was first discovered in the context of cosmology. If you look at space-time near a generic space-like singularity, you find that the light cones collapse to become lines. This can be thought of as the limit as the speed of light goes to 0, or the anti-Newtonian limit. What this means, in turn, is that nearby spatial points don't communicate with each other. What that means, if you stick that into the Einstein field equations, is that the space-time becomes locally Kasner, or technically it shows BKL behavior, which is locally Kasner, but with the axes of anisotropy changing chaotically with position and time. Now that's near a space-like singularity, but there are indications both from the short distance approximation of the Wheeler-DeWitt equation and from looking at the effect of fluctuations of the stress-energy tensor near the Planck scale, that this may be true generically at very short distances in quantum gravity.
The second one.
Yes. So the relevance of this is that, as I said, Kasner space is almost 1 plus 1 dimensional. That is, if you look at the region explored by a geodesic near t equals 0 in Kasner space, you get a long, thin cigar shape that successively becomes thinner and long and stretches as you approach t equals 0. Actually, the same behavior as t becomes very large. So Kasner space, in some sense, is nearly 1 plus 1 dimensional. In particular, you can write out a metric for Kasner space, and in this limit, the metric splits into two pieces. There is a space-time piece with one characteristic scale, and an orthogonal piece with a different, much smaller characteristic scale. If you plug this form into the ordinary Einstein-Hilbert action, you end up with an action which is very nearly that of a two-dimensional conformal field theory, in which the orthogonal metric, the H, is a conformal field living in a 1 plus 1 dimensional space-time. Now, various people, including Gerard, have looked at this in different contexts, in the context of the Eichenal approximation. But perhaps this is a generic feature of space-time at short enough distances. If so, maybe this could explain why you should expect a two-dimensional fixed point in asymptotic safety. Maybe this is pointing us in a direction that will let us understand dimensional reduction. Well, or maybe not.
This is only for the class of whether matter doesn't matter, as you
For
like the type 1, type 9, and all those.
No, this is generic behavior for the short distance limit of the Wheeler-DeWitt equation. In the short distance limit, the Wheeler-DeWitt equation is dominated by BKL solutions.
It's only for the class that matter doesn't matter. For example, Robinson, Walker, Friedman, you need matter,
So,
and you see matter all the way down.
yes, but those are exceptional if you look at the limit as L Planck goes to infinity of the Wheeler-DeWitt equation, coupled with almost arbitrary matter. In the L Planck goes to infinity limit, it is dominated by BKL.
Even with matter.
Yes, even with matter, unless you have an enormous number of matter fields.
That includes also Friedman, Robinson.
Yeah. FRW is exceptional, that you have to fine-tune the symmetries. Okay. Well, anyway, let me just end with let me just end by saying that we don't know the answers here. And I hope that somebody maybe in this room tells me the next step. Thank you.
Yeah, so just sort of a question and a comment on sort of the BKL conjecture and the thing you were saying at the end there.
Yeah.
The first thing is you say that in a neighborhood of t goes to 0, your geodesics only going to explore one dimension. However, in any epsilon neighborhood of t equals 0 within the BKL conjecture, the Casmus solution is unstable. And you will go through an infinite number of tau transitions. And therefore, any geodesic will in fact explore all 3 dimensions an infinite number of times in any epsilon neighborhood.
That's actually good. I don't want to actually get to t equals 0. I mean, I am going to assume that there is some sort of Planck scale cutoff. But the fact that you have a large number of transitions is the only thing that makes this, that leaves there a good possibility that this could agree with observation. Because if you don't have a large number of transitions, then you have breaking of Lorentz invariance on a scale that probably would have been seen by now. The transitions smear that out. I have a student who's actually looking right now at what effects this has on light propagation. But you probably need at least a very large number.
So address the point that was about matter mattering, which made mention a second ago. If you introduce a master scalar field or a stiff fluid into these equations, it does turn off the mixed matter behavior entirely. This is where you quiescent.
Yeah, I think that that's true classically, but if you look at least at the short distance approximation to the Wheeler-DeWitt equation, the momentum squared term comes in with 1 over L Planck squared. The matter comes in with, I believe, a 1 over L Planck. I'll have to go, but you have to rescale things. I don't promise that that's true, but I did look at it once, and the scalings are different enough that at least in the L Planck goes to infinity case, the momentum term dominates over ordinary matter terms. Yeah.
More questions or comments?
No, see, if many people actually suspect, and I do also, that space and time basically become discrete at the small enough distance scale. So suppose you look at the volume,
Yeah.
which only contains 6 space-time points. What does the notion of dimension then mean?
Well, one answer to that is this Meerheim-Meyer dimension, which was invented explicitly to deal with the case of discrete points. If you count the wrong button. If you count the number of points in a discrete but causal space-time in a causal neighborhood of a point, then the relationship of that, the number of points to the number of points in a sub-neighborhood, is something that in the continuum limit gives you a unique and simple function of dimension. So that allows you to define a dimension that looks right as the number of points becomes denser.
But would you say that if once you look at large enough spaces like that, you just get 4 dimensions as usual? At very small scales, you get basically nothing anymore because you have just single points. In between,
Right.
it seems that the number of dimensions is rather inaccurately defined. Is that true?
Well, again, it depends on what question you're asking. For example, you can ask what quantum field theory looks like on a causal set. And one way to do that is to define a discrete Laplacian or a discrete D'Alembert that has the right continuum limit. And if you do that and you look at the behavior of that Laplacian at scales that are big enough that you have a number of points, but small enough that you don't have a continuum or a four-dimensional limit, you find that that Laplacian goes from logarithmic behavior in the geodesic distance between 2 points up to the ordinary four-dimensional behavior as you increase the number of points. So physically, I think that probably is an answer to your question, because physically, presumably, what we actually observe when we make measurements is all two-point functions of fields and things of that sort.
Steve, could you turn back to the slide where you mentioned the non-Gaussian part, asymptotic silence?
Okay. Where was that? Yeah, this one. Mm-hmm.
So, a non-Gaussian matter field source, as we were discussing after lunch. I'm just curious whether two things. Whether it would force out a stochastic component in the wave equation. Now, before that, I should actually ask you the question. When you write down in the string of proper time, usually that when you go from the green function to the heat kernel, and then the leading term, as you wrote down, is s to the minus d over 2, then the residual expansion and so on. First of all, that's actually a fictitious time, right?
Right.
But then my question, you seem to have said that that's a rather general form, the leading s to the minus d over 2, and then you can draw a conclusion about dimensional reduction. So there are two questions. The simpler one is this one, that why do you say that? It's based on using a wave operator, right?
Right.
It's preconditioned upon that, right?
Yes.
That leads to my second question. Do you foresee if we have sort of non-Gaussian noise, whether you have anomalous diffusion and maybe some stochastic component in the wave operator could be considered?
Okay, so the first question is easier to answer. The answer is that it is absolutely true that the heat kernel and therefore the spectral dimension depend on your choice of Laplacian. And there are situations in which the simplest choice is known to be wrong. For example, in causal set theory, the simplest the choice based on ordinary diffusion doesn't give you a Laplacian that has the right continuum limit. So it's in causal set. And in Horjava-Lifshitz gravity, probably you need Laplacian you need a delta to the fourth to understand the quantum behavior. So the answer there is the answer there is that it depends on the physics, and that if you could define the physics clearly enough, I could answer the second part of the question, but I don't know. I know it's certainly true that fluctuations of the stress energy tensor are highly non-Gaussian. It's true that these back react to cause highly non-Gaussian fluctuations of space-time at the Planck scale. These have all sorts of weird results, like it means that if you're looking at the focusing of light near the Planck scale, you get sharp focusing almost everywhere, which is what leads to this idea that perhaps you get local asymptotic silence. Putting that back into a heat kernel, I don't know, because I would have to, you would have to tell me what kind of matter and what kind of propagation you're looking at, given that one could maybe look at these fluctuations and see how they correct the propagation. And yeah, it's possible that you would get something that's rather different from the ordinary Laplacian.
Yeah. In connection with your comment about the many Cassel-Vances and you needed them to save Lorentz invariance, what experimental evidence are you relying on to say that you've got to have that?
There's a huge set of tests of Lorentz invariance coming from, for instance, looking for frequency dependence of light from quasars, a frequency dependence of synchrotron radiation, relations between times of arrival of neutrinos with different energies. I mean, Dave Mattingly has a 100-page review of this, and probably there are 100 more pages that could be added to that.
And this is pushing it down below the Planck length, is it? The Lorentz symmetry holds well below the Planck length of it? But can you give
for corrections to dispersion relations that are first order and I believe now second order in momentum, the limits are now at or below the Planck length. Pardon? For standard model fields, yeah. Yeah, although I think that there are some claims now from the gravitational radiation observation of limits of at least some kinds of Lorentz breaking from there. Yeah. But so, I mean, here you could look simply at light propagating through a space-time that is locally two-dimensional. Which would be a drastic change in the dispersion relations. The thing is that the tests are almost always done in terms of what's called systematic Lorentz invariance breaking, which is breaking in which there's a single preferred direction. When you have non-systematic breaking, where you have preferred directions that are varying rapidly in space and time, the limits are much, much worse. As I said, I have a student who's looking at this, and we might be able to say more soon.
Thank you.
And I'm afraid we don't have more time.
That was fun.
You told me to switch it on, and I forgot. Yeah, so thanks to the organizers as well for the kind invitation and for the very interesting conference. Yeah, so this is another dimensionally reduced talk, following from the very nice one we had from Steve Carlip before. Yeah, so here I'm going to focus on what could be the signature of dimensional reduction within a cosmological context. What I'm going to talk about is based on this series of papers in collaboration with Giovanni Amelino Camellia and Michele Arzano in Rome and João Magueijo in Imperial College. In particular, I would encourage you to read this nice essay written for the Gravity Research Foundation, where you can find the short and nicely written version of what I'm going to talk about. So since this is the day's last talk, and everyone is probably tired, I decided to start from the conclusions so that then you can relax. However, if you plan to be attentive during the talk, then don't listen to this part, and I'll repeat it later. So what I'm going to present is a study where we look at the primordial perturbations in models that present dimensional reduction to 2 in the ultraviolet. In particular, in the first part of my talk, I will consider the case that is inspired from Orava-Lifshitz models, where you have a dispersion relation for the perturbations that is of this sort. And in this specific case, things can be worked out fully, and we find that cosmological perturbations are scale invariant already inside the cosmological horizon, and then they keep being scale invariant outside with no need for inflationary expansion. And an interesting observation is that you can redefine the time variable so that the dispersion relation looks trivial. And this is what I'm going to call a rainbow frame. And in this frame, we will see that the perturbations are only conformally coupled to gravity. So they do not feel the universe expansion in particular. And there is no horizon. And this is why they are scale invariant inside and outside the horizon already. In the second part of the talk, I'm going to see if this nice picture can be extended to more generic case where you still have a running to 2 dimensions in the UV, since we have seen from the previous talk that this is the interesting case. So what it turns out that we can still show that perturbations are always scale invariant. However, only in flat spacetime. So this is not easily extendable to the cosmological context. However, if you assume that in the UV the perturbations are still conformally coupled to the expanding background, then this result is enough. And you have that cosmological perturbations are always scale invariant in theories that in the UV run to 2 dimensions.
So the first part, the perturbation is off the Holography gravity, or what's the background space-time?
Yeah, so I'm going to discuss the details. So this is just to give the take-home mesh, so all the details are... Yeah. All the details are coming. Yeah, sure. Okay, so now we go on with the actual talk. Okay, so this is just one slide to review the formalism normally used for cosmological perturbations for people who are not familiar with it, and also to set the notation. So this is just standard cosmology. So what you usually do when you want to look at when you want to study the power spectrum of perturbations, you start from the second order action, that you derive from the Einstein-Hilbert action. So second order imperturbation, it usually looks like this, where V is the scalar perturbation, and it's related in this way to the comoving gauge curvature perturbation. Then what you usually do is to go in Fourier space and write the equation of motion from the second order action, that is of this form here. And you see that you have two terms here in parentheses. The first term is a pressure term, and is the one that dominates at small scales, so inside the horizon, while the second term here is the Jeans instability term, and is the one that dominates on large scales, so outside the horizon. So an easy way to find what is the spectrum of perturbations is to solve separately the equation in the two extreme regimes, so the one well inside the horizon and well outside the horizon, and then match the solutions at the boundary. So here is how you do it. So at small scales, so you only have this term here. The solution takes this form because it's just a standard harmonic oscillator. On the other hand, if you are on large scales, this is the term that dominates, and you can generically say that the solution can be written with these ansatz. So it's dependent on the scale factor, A, and some function of K, that is the wave mode here. Then what you want to do is to match the two solutions at the boundary. So when omega, which is the frequency, is 1 over eta, which is the conformal time. And it turns out that in the standard case, the matching only works if you put yourself in a de Sitter background, so that the scale factor takes this form. And then the function f of k has this dependence on k. From this one, once you have these, then you can compute the power spectrum. Do you see the last lines in the slides? Yeah? Okay. So you can compute the power spectrum for the perturbation, that is P of k, that is defined in this way. So it's k cubed times z square. And it turns out, if you just put these things inside, that outside the horizon, the power spectrum is scale invariant, which means that has no dependence on k. Okay, so this is the standard story. What we want to do is to introduce quantum gravity effects on the perturbations. So we assume that they propagate according to some modified dispersion relation, which takes this form here. So here, lambda is the 1 over lambda is the quantum gravity scale. Gamma is some numerical parameter that tells you what is the power of the P modification. So for gamma equal 2, we recover the Orava-Lifshitz dispersion relation in the case where the critical exponent is 3, which is when the theory is power counting renormalizable. It has been shown that this dispersion relation here is associated to a running of the spectral dimension to 2, to a generic running of the spectral dimension for any gamma. And in particular, for gamma equal 2, the spectral dimension runs to the value of 2, which is the interesting one. And as we have seen in the previous talk, this is a value that is showing up in several theories of quantum gravity. So the gamma equal 2 case here is the one we want to watch out for. And then I have one last observation before we go on, which is that the regime where the perturbations are generated is such that what actually counts is only the UV form of the dispersion relation, so we can actually neglect the simple p-square part. And more in general, if you had the lower powers of these of momenta also in the correction, they wouldn't count. So what counts is only the ultraviolet form of the dispersion relation. Okay, so now we can go back and play again the game for computing the power spectrum. So I start from the same equation of motion as before, which means that so to answer your question, means that I am assuming that the original action is the Einstein-Hilbert action standard. And the only thing that is changed is how the perturbations propagate. So what changes here now is that since we have a different dispersion relation, the speed of propagation c becomes momentum dependent. And in particular, we have to be careful about the fact that the dispersion relation is written with the physical momentum p, which is related in this usual way to the comoving momentum k. So they are related via the scale factor. And this is the form that this is the form for the speed of propagation. Then again, we look at the equation. We start solving for the small scale, so well inside the horizon, and we find that the solution now takes this form, which is formally is the same as before. I neglected the exponential, which is just a phase that was here. So what's important is the amplitude. So this is the form that we had before, but now c is k-dependent and also scale factor dependent. So once we put everything inside, we get that this is the general form for the perturbation. And if we compute the power spectrum here of the perturbation at this point, using again the definition I showed before, then it turns out that this is what you get. So this is for a generic gamma. And as we said, gamma equal 2 is the interesting value. And you can see easily that for gamma equal 2, the scale factor here cancel and the k factors here cancel with this one. So you get a scale-invariant power spectrum. Regardless of what is your actual scale factor as a function of time. So you don't need to assume that you are in the Sitter background, because the scale factor just cancels out, and you just bring these scale invariants automatically outside the horizon. So I mean, the matching is trivial in this case. This result was also found in using a different method, more rigorous probably, by Mukoyama in 2009 for the Orava-Lifshitz case, for the gamma equal 2 case, and he also found this scale invariant power spectrum. Okay, so we see that we have these scale invariants, and yeah, before we go on, let me also say that we can also nicely match. I mean, we can connect some of the parameters of this simple model to cosmological observables. So, for example, we can show, and I will come back to this later in more detail, that the amplitude of the spectrum is actually linked to the ratio between the Planck scale and this quantum gravity scale lambda. And in particular, the fact that we know that the amplitude of the power spectrum is 10 to the minus 5 from observations tells us that the ratio between the Planck scale and the lambda should be this one. Moreover, if you assume that the tensor perturbations propagate with the same law, but maybe with a different coefficient lambda in front here, so that the actual speed of propagation of tensor modes and scalar modes is different, given by some ratio b, then the tensor to scalar ratio, so the ratio between the amplitude of the tensor power spectrum and the amplitude of the scalar power spectrum is simply given by the ratio of the two speeds of propagation. And again, these from current constraints, we know that must be less than 0.1. Another thing you might be worried about is that I showed you that we can get scale invariants, but we don't want to get exact scale invariants. We want to get slight departure from scale invariants. So this NS is the exponent that appears here, so we can write the power spectrum as k to the ns minus 1. So you see that if ns is 1, then the power spectrum is scale invariant. Otherwise, the value of ns tells us how much are we far from scale invariance. And current estimation of this parameter is this one here. And again, on this topic, I will come back at the end of the talk. Here, let me just mention that a few easy ways to overcome the problem is just assume that the gamma parameter is actually running with frequency, so that when perturbations are formed, the gamma is not actually exactly 2, but it's close to that value. Oh, sorry. Yeah. Yeah, so we can assume either a slow running, or we can assume directly that gamma is not exactly 2, but is close to 2. And in this last case, so assuming that gamma is not exactly 2, then we get that the fact that we are independent from the background that I've shown you before, so the fact that the perturbations were scale invariant already inside the horizon and they would just keep scale invariant outside, does not hold anymore. You get a dependence, an explicit dependence now on the scale factor A. So again, playing the game I played before, from matching of the modes inside and outside the horizon, you find that this is the form for the scalar perturbation over A. But now there is an explicit A dependence here for a gamma different than 2. Then, in general, you can write the scale factor in a way that is dependent on the equation of state parameter. So epsilon here, so W is the equation of state parameter, and this epsilon is defined in this way. This is just a notation that is standard in cosmology. And then you can find that there is, in general, a relation between the scaling, between the departure from scale invariance, the power of the deformed dispersion relation, and this epsilon that is related to the equation of state parameter. And you can also go ahead and use this relation to make a plot of the spectral dimension resulting from the dispersion relation with the given gamma, which are related in this way, and the equation of state parameter of the universe in the universe. And this is what you would get assuming the 1 sigma constraint on NS from Planck. Okay, well, this is one option, but it's a bit, I mean, it's a bit made up because I'm just modifying with gamma, so I will come back later on this to see if there is a more elegant way to solve the problem. Okay, so we have seen that we have these scale invariants independent of the expansion of the time dependence of the scale factor. We want to understand a bit better why is this happening, and a way to do it is to change frame in which we write things. So we start. So we have seen that the speed of light, speed of propagation of perturbations is dependent on k and a if the dispersion relation is modified in this way. But we can change the time unit that we are using to make the speed of propagation a constant. So this is just this simple change of coordinates. Of course, now the time unit is going to be dependent on energy, and this is why I call this a rainbow frame, because it's energy dependent. so in these new variables, we can write again the second order action. So this is what we had before in the Einstein frame. Now it's written in terms of zeta, which was related to V as V over zeta equal V over A. And I can make a simple change of variable to go to this rainbow frame. And now you see that here, instead of the scale factor A square, I have this Y square, which is some rainbow scale factor. And here, the speed of propagation c has disappeared because it's now equal to 1. In this frame, the equation of motion takes this form. So it's very similar to what we had before. It's just that now we have it written in terms of this y variable and time, and this tau time. Okay, this is the same equation again. And now if we look better at what is this rainbow scale factor doing, so it's related to the original one as a square root of c. We put in the explicit expression for c that we had from before. And the interesting thing is that for gamma equal 2, you see that this rainbow scale factor becomes time independent because again, the standard scale factor A cancels out. And this means that this component of the equation that we had before is just disappearing, so that we have a standard harmonic oscillator that is, and this equation does not have this term that depends on time. So it's not true anymore that we have some equation that is valid inside the horizon and some other equation that is valid outside the horizon. So we have just become, in this frame, you see that the theory it has just become blind to the fact that there is an expansion and that there is an horizon. And it is in this sense that I said that perturbations are conformally coupled to gravity in this model, because in this frame we see that the equation is just written as it would be written in the flat space-time. And once you have this, then it's very easy to work out what is the power spectrum. And of course, we are going to get the same result of the scale invariance that we got before, now in even a simpler way, because the equation is this one. The solution is now universal. We don't need to do modes matching inside and outside the horizon. And just putting all the expressions inside, you can see that the power spectrum is independent of k. So we get again the result about scale invariance. Okay, so let me summarize the results of this first part of the talk, and then we can go to the second part. So what we have seen is that for a specific model, which is this model in which perturbations have a dispersion relation of the Orava-Lifshitz type with the special value for gamma exponent 2, so that the theory runs to 2 dimensions. We have that there are 3 things that happen at the same time, and so we might expect that they are related. So the things are that we have this UV dimensional reduction to 2. We have that perturbations are scale invariant outside and outside the horizon, and we have that perturbations are conformally coupled to gravity. All of these in the ultraviolet, of course, because we are in that regime. So I mean, it's natural to wonder whether this is just an accident of this specific model that we happen to study, or if there is something deeper here, and this connection between conformal invariance and the running to 2 dimensions and the scale invariance of the power spectrum is something that sounds good, so it's worth investigating a bit more. So in order to do this, I want to consider more general theories which present the same phenomenon of dimensional reduction. The way I will talk about them is by looking at the momentum space dimension. What I mean by this is that, so let me take again as an example the one we have been studying until now. So if I have this dispersion relation, I can always change the momentum, energy momentum variables in order to make the dispersion relation trivial. And in this case, this is the obvious change of variable that you would do. Of course, if you do this, in order to, for everything to keep being consistent, you also need to modify the measure in momentum space. And so you would go from the usual spatial part of the spatial momentum measure, which is this one, just applying trivially the change of variable, to this other momentum space measure here. And this again is only valid in the UV approximation, so when this term dominates over this one. And from this you can read a very simple and naive version of dimension, which is the Hausdorff dimension for momentum space, just remembering that what you would usually have here is P2, the dimension of momentum space minus 2. So just by comparison, you can deduce that the dimension of energy momentum space is related to the gamma exponent here in this simple way. This notion of dimension matches the value of the spectral dimension, of course, and you can easily verify that for gamma equal 2, this dimension is 2. So again, we are saying that the model runs to 2 dimensions, but now looking at this momentum space dimension, which is more easy to deal with in what follows. So the sort of, so before, I want to just open a parenthesis to show you the sort of more general models that I might want to consider that are not of this simple form. One example is that we might want to look at dimensional reduction in a case, so the dispersion relation I showed before is of course breaking Lorentz invariance, and we know that Orava theory is breaking Lorentz invariance, but we can look at modified dispersion relations without necessarily breaking Lorentz invariance, but just deforming what are the relativistic symmetries. So this is a milder departure for special relativity because it's still a relativistic theory with deformed transformation rules. So one quite well-studied example is the case where momentum space, instead of having a flat metric, has a de Sitter metric. So in particular, the metric on momentum space takes this form here, where here I'm using the analogous of the cosmological de Sitter coordinates, but in energy momentum space. From this measuring momentum space, you can derive the measure on momentum space in the usual way as a square root of the determinant of the metric, the dp. So here, capital D is the dimension of the spatial part of the momentum space. And in this particular case, the measuring momentum space would be this one here. Now, I mean, since de Sitter is still a maximally symmetric manifold, we still have the full number of relativistic symmetries. However, they are not anymore the usual Poincaré symmetries, but they are the isometries of the de Sitter manifold. So, of course, you need also to modify what the dispersion relation of particles is, so that the combination of the dispersion relation and the measure of momentum space builds a relativistic theory under de Sitter isometries. And in particular, I will take the Laplacian of the theory to have this form, where CL is this one. And you can show that this is indeed invariant under de Sitter isometries. For people who are a bit more familiar with this, this is the Casimir of the kappa Poincaré algebra. So this is a a realization of the Kappa-Poincare symmetries on a momentum space, and it turns out that it's a de Sitter momentum space. So this is one possible realization of another theory. Again, we can show that this of another theory where we have a deformed dispersion relation, but the interplay with the modified geometry of momentum space still keeps the relativistic invariance. And also in this case, we can show that there is a dimensional running, and I will do it looking at this momentum space dimension. And the way to do it is to make a change of coordinates that here is a bit less trivial than before, but still quite easy. So you have to do it in 2 steps. First, go to these radial polar coordinates. The measure becomes this one. One second. Here we have a gamma exponent. So this is c times 1 plus c to the gamma. And this is the gamma that appears here. And via this 2-step change of coordinates, we end up with a theory that has a trivial dispersion relation again, but it's still a non-trivial measure that takes this form. And again, from here we can simply read the measure of momentum space by noting that all of these should be the total dimension minus 1. And in fact, we can see that the momentum space dimension for this model is this one, where D is the original spatial dimension, and gamma is the power of the Casimir that appears here. And in particular, in this case, we have that the theory runs to 2 dimensions in the UV, when if we start from a theory that originally is in 3 plus 1, and again, if the exponent gamma is equal to 2. So in the following, I'm not going to use this specific theory. This was just to give you one example of how other models could fit into this framework. Okay, so what I want to discuss now is what happens to vacuum fluctuations for theories that present a running in the momentum space dimension. And I will do it assuming that I'm already in the variables where the dispersion relation is trivial and I have a non-trivial measure in momentum space, so which is the final step that I had here, for example. Here, EP just stands for the on-shell energy. It's just using this notation. So if I want to do, if I want to compute the spectrum of vacuum perturbations here, of course I need to start from the, I can follow very closely the standard procedure that you would use to quantize a scalar field, just making sure that the form measure is put in the correct places during all the procedure. So of course I want to start from a covariant on-shell measure, which is what I would do in a standard case. In the standard case, this would be the covariant on-shell measure. In this case, I have the deformed momentum space measure here. Then I can simply write the field expansion in the usual way, remembering that the integral now has a modified measure. And again, the one particle normalization is as usual proportional to a delta, but the delta related to the deformed measure. So this is the property defining the delta function now. And this is what you would have in the standard case. Now I want to compute the power spectrum. In particular, I want to compute the power spectrum that is the one used in cosmology, which is a dimensionless power spectrum that is defined by this relation here. So this is the dimensionless power spectrum that is just that is dimensionless because I put here the correct powers of T so that the measure is dimensionless, and Z is related to a standard scalar field just by a factor of the Planck length. So Z is proportional to the scalar field. In order to compute this, I only need to do an intermediate step, which is look at the covariant power spectrum that is instead defined in this way here. So it's the vacuum expectation value of phi square, and the integral is written with the modified momentum measure. And by comparing these two integrals here, and using the relation between z and phi, I can relate the cosmological power spectrum to the scalar field power spectrum, to the covariant power spectrum. And you see that they are related by some factors of Planck length, a p, and the modified measure mu bar. Then I can also explicitly compute this vacuum expectation value just using the expansion here and this this one particle normalization here. And it turns out that this covariant power spectrum is always 1, regardless to what the measure I put here is. So in the end, I have a nice expression for the dimensionless power spectrum, only in terms of the deformed measure, because this factor is just 1. More specifically, I can write an explicit version, an explicit form for the momentum space measure. So the general form that it will have is this one. So it's some power of the momentum that depends on the dimension of the momentum space dimension of the theory, and the quantum gravity scale, and then this is the on-shell energy. This is what you would have in the standard case in 3 spatial dimensions. You can compare and see that it works. And then you can use this relation for the power spectrum to work it out fully, and you get this thing here that is only dependent on the dimension of the momentum space. Okay, here it's just written in a nicer way. And in particular, you can see that if you start from a theory with 3 spatial dimensions, and you have a momentum space measure such that the momentum space dimension is 2 in the UV, then the power spectrum is scale invariant. And in particular, we find again this relation, the fact that the amplitude of the power spectrum depends on the ratio between the Planck length and this other quantum gravity scale. So it depends on the hierarchy between the two. So this is now a general result saying that whenever we have a model with 2 dimensions, in 2 momentum space dimensions, then we have that vacuum fluctuations have a scale invariant power spectrum. And here let me just make an observation. So in general, the power spectrum will take the form that we have seen already. So with this NS telling us how much the power spectrum is departing from scale invariance. And by comparison of this relation with this one, we can see that there is a very simple relation between the spectral index and the momentum space dimension. So I would say that this could also be, the reasoning could be reversed, and this could be used as another definition of dimension. So we could imagine about measuring UV dimension by looking at how much the vacuum fluctuations depart from scale invariance. Yeah, so as I mentioned at the beginning, this construction here that I've done, it's done in a flat space-time. We have not done quantization on curved momentum or concurved space-time here. So this is it would be very nice if we could extend this result to a curved space-time, so that we could apply this general thing to the cosmological context. So here I go to conclusions. So this is what we have learned from the first part of the talk, which is that in one specific model we have these 3 nice things happening at the same time, which I have already discussed. What we know now in a more general case is that we still have UV dimensional reduction. We can consider more general models with UV dimensional reduction to 2. we have nothing to say about this for the moment, and we have that again, dimensional reduction to 2 corresponds to scale-invariant power spectrum. However, only in the flat space-time case, and not in this nice in a general, for example, Friedman, Robertson, Walker background. However, at this point, it's tempting to conjecture that actually gravity is conformally coupled in the UV in any case, so not only in the one model that we have worked out fully. And then in that case, the result about scale invariance would again hold in the cosmological context, not only in the flat space-time case. So this would motivate the proposing that actually in the UV gravity has to be conformally coupled to perturbation, or more in general to matter. And perhaps here is just speculation. So of course there must be some mechanism that during the transition from the ultraviolet to the infrared not only increases the number of dimensions to 4, but also breaks this conformal coupling of gravity. And maybe the way this happens is also responsible for the fact that what we observe is not an exactly scale-invariant spectrum for cosmological perturbation, but an almost scale-invariant one. So probably, I mean, one could speculate that the mechanism that's doing all of these also is responsible for this slight departure from scale invariance. Okay, I'm done. Thank you.
So in the first part you were using the expression relation for level efficiency gravity, but I got the impression you were using the equations of motion and the perturbations around coming from Einstein-Hilbert's.
So the background theory is Einstein-Hilbert. The dispersion relation that I'm using is the one that is inspired from Orava-Lifshitz. It's not. I'm not doing the full Orava-Lifshitz gravity. However, there is. I mentioned that paper from Mukoyama, and he was doing more proper work and finding the same result about the scale invariance.
So the general features would be relevant to the precise equations of motion.
So can you say it again?
The features that you were highlighting would be insensitive to the details of the equations of motion that you would obtain otherwise.
Yeah. If you modify the equation of motion, then yeah, you would get a different story. Yeah.
So the component variance is only approximate, right? Because it happens to be and you neglect the lower order operators.
Yeah.
So that means that the lower order operators would make that
yeah, that's where they would be important. Yeah, I mean, all of this is in the.
How large?
Not yet, and I mean, it's not clear how to do it. It's something we are thinking about, and I mean, it's very interesting because the hope is that exactly these lower order operators do all the job of breaking the symmetry and giving you the departure from scale invariance and so on and so forth. In the regime where the transition happens, they would be relevant. So I mean, this is an interesting thing.
What about inflation?
Here there is no inflation.
Yeah, but you would need inflation for more than just to generate a flat power spectrum. So what about all the rest?
You mean?
Well, specifically, if you have a model for particle reduction, inflation usually means.
Yeah, no. About that, not yet. Yeah, you have to put in more detailed, more ingredients to have the full picture. This is saying that as far as the perturbations are concerned, you don't need to have the inflation. But you also have seen that the result that we get is independent of the background. So at some point you could think about.
Like a reason, it looks like you take a few desirable things and put them together.
Mm-hmm.
You start with presumably the 4D, four-dimensional space-time,
Yeah.
use of perturbation, or conformal fields, recognizing the way. But then how let the gamma, right, be a free parameter, but I can visualize the situation where gamma turns to 2. Do you then have to redo the calculation of perturbation of a two-dimensional space-time, which would give you a totally different equation?
Well, the dimension that I'm talking about is this notion of spectral dimension, or maybe this notion of momentum space dimension. It's not saying that the actual space-time has to be. I mean, again, we are at the question of what do we mean about dimensionality in these models. This specific case in this case, what you have is that there is this spectral dimension that is related to some diffusion process in the Euclidean manifold associated to the model that behaves as a diffusion process in the same way as if it was in 2 dimensions. But it's not saying that.
I understand that part and how you define spectral dimension.
Yeah.
Extent that it could be defined, right?
Yeah.
But then you're drawing an inference that's based on the 4D perturbation.
Yeah. Yeah, but it's I mean, it's not that the 4-dimensional space-time coordinates disappear. I would say that the way particles propagate is as if they were in a 2-dimensional setting, but it's not that actual space-time is 2-dimensional. So perturbations or
Perturbation is still off a 4D
yeah.
space-time.
I'm not sure if I answered, but yeah, we can discuss more.
More questions or comments? Okay, if not, we can close the session.